Okay, so we're going to start our very final unit of the GCSE course, and this is the speed time graphs unit, often called pre-calculus. You'll also recognise the fact that speed time graphs can be called velocity time graphs. So the two names are interchangeable, so just be aware that you may see either used. Just want to go through a few definitions for you. So velocity in the first place just means speed in a certain direction. And what we can use a velocity or speed time graph to calculate is acceleration. And actually the gradient of the graph tells you what the acceleration is. The formula for acceleration then is the change in the velocity divided by the change in time. Again, that is still the gradient formula. It's just going to be the change in the y-axis divided by the change in the x-axis. Okay, but I'll show you some of these in a more formal example. Again, just a few more key bits of information. So a reminder that velocity time graph shows speed and direction over a given period of time. It's key to be recognizing that 5 meters per second and negative 5 meters per second are the same speed, but therefore in opposite directions. As we said, acceleration is a rate of change of velocity over time. The most common units you'll see are meters per second squared, and again, you will have come across that in science. As we said, the gradient of a velocity time graph shows us acceleration and or deceleration of an object, so just recognizing the two there. As with gradient, the steeper the graph, the greater the acceleration of the object is. And just to be mindful, a straight line shows an object has constant acceleration, and a horizontal line means the object is moving at a constant velocity or speed. Okay, right, so to start off with here, we're just going to have a look at what you've seen before in terms of a distance time graph on the left-hand side, and therefore the new one that we're going to look at now, which is going to be a speed time graph. They look very similar, they're easily confused, so you do need to be careful. A distance time graph is often around a grade 5, and you'll find that near the start of an exam paper. However, a speed time graph is often far more complicated, with different things to consider, and often around a grade 8, 9, and therefore nearer the back of an exam paper. As I say, the two main features that are the same is on the x-axis, it is time on both. However, the y-axis, one will always say distance, which is your distance time graph, and the other one will be speed or velocity for a speed time graph. And therefore, what we can calculate and work out from these graphs can be very different as well. Again, looking at the left-hand side, so the distance time graph, we've just got our regular key features that you should recognise. So a straight line with a positive gradient, i.e. the line AB or the line CD, that represents the movement away from the starting position at a constant speed. The horizontal lines then, so B to C and D to E, they represent the fact that we're not moving anymore and we're stationary at that point in time. And the last part is a straight line with a negative gradient. That represents movement back towards our starting position at a constant speed. So that would be E to F or G to H. If we're then having a look at the speed time graph, so this is where it's telling us something different, then a straight line with a positive gradient is actually going to represent constant acceleration. It's not constant speed, it's constant acceleration, which means over time it's getting faster and faster. So you do need to be mindful of that. Okay, so it is faster and faster and not a constant speed. Constant acceleration is what's happening at that point. However, a horizontal line, like we have at the top here, okay, that's showing us at that point that it's movement at a constant speed. So between the 20 seconds and our 50 seconds, it's moving at a constant speed of 8 meters per second. And then the last part of the graph here, where we've got a negative gradient, that one's representing constant deceleration. Okay, so it's accelerating in the other direction, so therefore deceleration at that point. You will also sometimes see a curved line for a speed time graph. This doesn't have a constant rate, okay, so therefore the acceleration is changing over time. So it's worth making some notes on your handout for this one so that you've got them to reflect back on. And then perhaps you can have a look at these two questions and then hit play when you're ready for me to go through them with you. So if we start looking at the first question, Journey C, Again, it's a speed time graph, so we've double checked that we've got speed on our y-axis. And for the first question, we want to work out the acceleration for the first 5 seconds of the journey. So it's just key to highlight that bit of information. The first 5 seconds of the journey, we then were going at the speed of 10 meters per second. And remember, for us to calculate acceleration, it was the change in velocity or speed divided by the change in time. So our calculation at that point is going to be basically the height of our triangle divided by the width. So your change in y over your change in x. So 10 meters per second divided by 5 seconds. This tells us it's 2 meters per second. And again, that's better off written as 2 meters per second squared. If we then have a look at the next question, so what was the deceleration at the end of the journey? So this is the point that we're looking at here. So in the last part of the journey where it's the negative gradient, we travelled over 20 seconds. And if you think about it, we've gone down at that point, so it's minus 10 meters per second. However, we're asked to calculate the deceleration. So the calculation is 10 meters per second divided by the 20 seconds, which then gives us 0.5 meters per second squared. And the reason for that is the fact that it is deceleration. If we were asked for acceleration, then it would be negative 0.5 meters per second squared. So just be mindful of the fact that acceleration can be written as negative deceleration. And then the last part, for how long was the speed constant? And you can see that is going to be where our horizontal line is at the top of the graph here, okay, between the 5 and the 15 seconds. And so it was 10 seconds at a constant speed. Right, so we're going to have a look then at journey D. So journey D, what was the acceleration for the first 5 seconds? So again, we want to highlight that bit of information on the graphs. The first 5 seconds is the first square. And in those 5 seconds, we were traveling at a speed of 4 meters per second. So again, to calculate our acceleration, it's the change in y over the change in x. So it's our 4 meters per second squared divided by 5 seconds, giving us 0.8 meters per second squared. Okay, for journey D again, after how many seconds did the speed stay constant at 4 meters per second? It's constant at 4 meters per second here, and that started at 5 seconds. So that's what that question is saying. After how many seconds was the speed at that point? And that's where it started from. So at the 5 seconds. And then our last part is then thinking about what was the acceleration between 15 and 30 seconds. And if we again highlight that key bit of information for us on here, then the 15 to 30 seconds is this triangle here. So between there, we've travelled 15 seconds at a speed of 6 meters per second squared. So that's come from the 10, take away the 4. And again, to work out our acceleration, it's just the gradient at that point. So it's the 6 meters per second divided by the 15 seconds, giving us 0.4 meters per second squared. Okay, there's one final question I want you to have a look at, and this time we've then got a curved part of our speed time graph. So again, just have a quick look at this one, think about what you could work out, and then hit play again when you're ready for me to go through it. Okay, so a reminder at this point, because we've got the curved line in the first part of the graph, that reminds us it's not a constant acceleration. So we're asked to work out the average acceleration between the 0 and 14 seconds. So to do this, again, we want to highlight the useful information. So we know between 0 and 14 seconds, that was a time of 14 seconds and a speed of 12 meters per second. We then actually just join those two red lines up with a chord, and we calculate the gradient of the chord. That will then represent the average acceleration at that point. Okay, so our calculation is then going to be the height divided by the width, so the 12 meters per second squared divided by the 14 seconds, and that comes out at around 0.857 meters per second squared, but I've rounded that one to 3 decimal places. So remember, for the part A, when you're working out average acceleration, it's then the gradient of the chord that you're working out. Okay, and then part B, so this one's different again. We want to estimate the acceleration at 4 seconds. So to do that, we need to draw a tangent, okay? And the tangent has to be specifically at the 4 seconds. So it's really important. So the first job is to mark the 4 seconds on the graph, okay? So 4 seconds is along the x-axis, and we're going to mark that point, which is my blue point there. We're then going to draw a tangent at that point, and the tangent has to just clip the graph at exactly 4. It can't be overlapping or a little bit off. It has to be exactly at that point for you to score marks on an exam question. Okay, so my tangent looks like that. And then to work out an estimate of the acceleration at that point, we then need to work out the gradient of the tangent. And we do that by drawing a triangle like we've done with the others. You want to try and make it as easy as possible, so picking 2 nice points. So you can see that I've done that there. This one is a nice point because it's a whole one there, and that's reasonably close to an exact point up here. And then we just need to calculate what the height and the width are. So therefore, my base goes from 2 seconds to 6 seconds, so I've got 4 seconds there, and it goes from the 4 up to the 8.4 there. So you just need to check your scale so you're reading it off accurately. And then at that point, you calculate your gradient. So it's the 4.4 meters per second divided by the 4 seconds, and that will give you 1.1 meters per second squared. It just got to be really mindful of the fact if you don't draw a tangent to work that out, you score no marks on an exam question, and you must be really specific that the tangent hits the exact point that they give you in the question. So in this case, the 4 seconds. Okay, have a go at the task set and let me know if you need help with anything.